So, hello there, guys. Today, we're going to talk about our last network fundamental talk, certainly in this series, and it is around multicast. So that is that famous thing that a lot of people have heard of, but probably don't fully understand. So we'll be going through a bit of a high-level view of what multicast is, what the fundamental building blocks are, and then running through them. So you've got the addresses, the registration protocol, and then how we route that multicast traffic across a layer 3 network. Now, some of it will be slightly technical, some of it won't. There'll be some examples, and we'll get to those later. But we will go through at least a high-level view of actual multicast flowing and operation. If you want more details, more specific technical details, well, I've done a talk both on IGMP and PIM, and I'll get onto what those mean later if you've never heard of those protocols. So before I even start talking about multicast, I think it's important to understand the kind of different data flows that you might have with inside a normal IP network. So you have the normal, unicast traffic flow that you would normally have. It's probably 90% of the traffic on a normal, standard, typical network. And that is, point to point. It's between one source and one destination usually. That is what we use typically for most of our communication. If you're pointing towards that BBC web server that I always keep on talking about to pull the homepage of BBC, well, that'll be a unicast request to that web server. So you can you would then get your individual unique response directly from the server. Now, well, maybe not directly from the server, but you get the concept. It is point to point. There isn't any extra devices that are going to get a response or that are going to send that traffic in that flow. Just those two. We then have broadcast. So as I've touched on it before in one of the previous videos around L2, broadcast is about flooding out a specific bit of traffic or traffic flows to a whole layer 2 subnet within a specific, within a layer 2 domain in a specific subnet. So we use the last address inside that subnet range to identify it as a broadcast destination IP address, and that can flow over a normal L3 network. And then when it gets to that specific end subnet, the devices and the routers and the switches will know, hey, this is broadcast traffic, let's flood it out across our network. That can be good sometimes. Maybe there's a specific reason why you would want to broadcast, but usually it isn't used past some kind of control messaging or those kind of things, because it's a little bit too dangerous to be broadcasting out traffic completely across the whole network. You never know what you've got on your network that could fall over with that extra little bit of data. We then have multicast, which is obviously the topic of today's talk, and that is all about point to multi-point realistically. Now there is additions where you can, do multiple devices can send traffic to the same group, and then that could go to multiple end devices. But in general, it is one host to a specific group, which then maps onto then multiple end devices. Now those multicast destination IP addresses are reserved. They are specific reserved IP addresses, and they have a specific range that you can use for that assignment of multicast. And so we'll get onto what those ranges are later. But that's multicast. It's from one destination, one source to potentially multiple destinations. Now, the one that I haven't mentioned on here is the concept of anycast. And anycast is not used too much, but it is a nice handy tool if you're doing things like working with CDNs, content delivery networks. So what an anycast address is an address, any standard IP address, but it is used in multiple places around a network. And the concept there is that you as a requester will go to your network, to your router. Your router will have potentially multiple entries for that same IP, and the router will then just pick whichever one is closest using the standard routing table. So it's a concept of unicast, but it's a different way of doing unicast. Unicast typically uses one very specific, potentially globally unique IP address on that specific end device. The concept of anycast is that you are actually inducing duplicate IP addresses to make sure that the layer 3 domain can actually select the closest one. This is a really good example for CDNs, content delivery networks, where they want to provide content really quickly to an end user. They can use the same IP address across the globe, and then ISPs and those kind of networks will be able to say, okay, what's the quickest way to get to there? Oh, okay, it's one hop over that direction. There we go. Rather than always going across to America or always going to Asia or Europe for the specific source of the traffic. So that's the type of data flows that we have. But what do they look like? Well, in the case of unicast, if we want to send to 3 devices, we've got to create 3 unique streams on the source. One that's going to add load to the actual source, so it processing all of that and duplicating those packets is going to be heavy lifting for that device potentially. It's also got to bear that in mind with the bandwidth between that source and the network switch that it's connected to, or the router that it's connected to, and all of the paths in between that source and those destinations. So maybe this link between this switch is only scoped for one single flow of traffic. Maybe it's a 10 gig flow. If you're sending 10 gigs as your, let's say a video stream, and you're sending it to 3 devices, well, that's 30 gigs of worth of traffic that you need to generate and effectively duplicate across the link. Maybe this link is only spec'd out for you to send that one stream of 10 gig. In this situation, then nothing would work properly because you would end up being congested and things wouldn't work. It also adds extra load to these switches because they have to process 3 times or X number of times the number of flows for the given number of destinations. So it's very inefficient. Now you do have broadcast, and that's great if you're working with flooding traffic within a specific layer 2 domain. So in this situation, an example might be, I want to flood a message or flood traffic to everyone in my specific layer 2 domain. Great. Broadcast is perfect for that application. But let's say only 2 of the devices actually here are really interested in this traffic. These 2 other devices are going to potentially fail over, or are going to have issues, or are going to have increased resource utilization. Let's take the example yet again that we're sending some kind of fat flow that is 10 gigs in size. Sure, this specific requested destination might be able to handle that 10 gig of traffic. But let's say for some reason some legacy device is on this layer 2 network, and maybe these only have like a 10 meg link. Now it wouldn't make sense to have those kind of devices on the same network, but let's say they have. As a result, if this device is really mission critical to whatever business you're in, and it's starting being flooded by 10 gigabits per second of traffic, well, one, the link between the switch and the device probably wouldn't handle that, and it's going to get congested. And then 2, because you've got that congestion, well, the device isn't able to handle it, and it isn't able to actually operate and do its actual function. You've also got to consider the extra load of traffic that is going to be on this destination. Maybe this device is legacy, as I mentioned, and it can't deal with that extra overhead of random packets that it doesn't know whether it needs to process or not. So there's those kind of things to take into consideration. And obviously, the next successor from that is then multicast. So you've got one single source. It is sending one single stream into the network. And then that one single stream is then being duplicated at the points that it needs to be duplicated. So this switch, if it's running IGMP snooping, a protocol that I'll touch on in a few moments, it will only duplicate the traffic to the given destination that has requested it. The same in the layer 3 network down here. This device hasn't requested it down here. So this router here doesn't even know that the multicast is in the network, potentially. Because there's no need for that router to actually see and understand that state. and process that traffic. It's only being sent to the relevant devices that have requesters behind them. So that's the benefit of multicast. You're being more efficient and more resource efficient. Obviously, you have a little bit of overhead with the protocols that you need to get multicast to actually run properly. But in the grand scheme of things, that is preferred over flooding out traffic or causing your source devices to duplicate traffic rather than it being duplicated by the network. So that's a bit of an overview of the different types of flows that we have. But actually starting to look into then multicast, well, how does it work? What are the building blocks that build together multicast operation? Because multicast is formed up of multiple different things that actually make it work. So we've got address ranges. So we've got to know, what's the group that we're actually requesting? Where are we sending it to? You've got registration methods. So how do you know that host A and host B are interested, but host C and host D aren't? Well, the way that we do that is what I just briefly mentioned was IGMP, Internet Group Management Protocol. So effectively what it is doing is it's collecting the state of and knowing who is actually interested on a local subnet layer. So this is working at a local layer to say, inside this subnet, these devices are interested, rather than saying across the network, one process of IGMP knows that those devices on that subnet are interested and those on that subnet. No, we have a process of IGMP which will run and it will manage state inside a local subnet range. You enable it facing a specific interface or specific VLAN. And so there are various versions of IGMP that actually support different functionality, and we'll get onto that a little bit later on. Now, there is an addition to IGMP, and that is IGMP snooping. So that can be enabled on some, not all, but some layer 2 slash layer 2 and layer 3 multi-layer switches. And so what that is doing is it's listening to these IGMP control messages, and without snooping, a layer 2 device would not know about that layer 3 multicast destination IP. So the natural way that a switch would deal with it is it would flood, because it can't read that information. It can't see that state because the destination MAC addresses are going to be unknown to it as well. As a result, IGMP snooping could come in and say, okay, we've received control messages from this destination, for example. This port is now interested in this traffic, so I'm only going to flood out of that interface. I'm going to ignore this one because we've not heard any IGMP traffic from it. And that's just a bit of an insight into how IGMP snooping works. I go into a tiny little bit more detail on the specific IGMP talk that I've done before. So if you're interested, go and take a look. But yeah, that's IGMP. Very briefly, I will touch on its actual operation a little bit later on in this talk. We then have routing decisions. We need to know how we're going to actually forward over this little layer 2 this layer 3 network here. Yes, this router knows that it's receiving multicast traffic, but how does it know where to send it? What's telling it, okay, forward out of this interface? Well, that's where you have to have some kind of routing decision for that multicast information. And that routing decision will be influenced by what is called PIM. At least that is the common option. PIM stands for Protocol Independent Routing, and it is a protocol that can manage multicast traffic in 2 or 3 different modes. And I'll get onto what those modes mean and how they operate later. But it is effectively sharing state around that layer 3 domain to understand who is requesting that multicast traffic and who isn't. And those that are requesting it, make sure that you forward it in their direction, basically. Now, I have mentioned PIM there. That is an independent protocol that it stands by itself. There is technically some extensions to OSPF that allow OSPF to manage multicast traffic. It is not really suggested to use them in actual operation because then they don't really scale that well. But it's just an FYI for those kind of trivia moments. And then obviously, finally, we have to have some kind of loop prevention. And I won't talk about this in too much detail because it is a little bit out of scope of this talk. if you want to learn more, go and take a look at the specific training on PIM and IGMP that I've done. But in concept, what this is it's the reverse path forwarding checks, and they are effectively saying, I've just received multicast traffic. So in the case of this router here, I've just received multicast traffic along this path. I look at the source address of that multicast traffic, and I compare that against my routing table. If I want to send traffic towards that that source, what exit interface am I going to look at? What exit interface is valid? Well, the interface that we just received the traffic on is valid. If we had received it from any other interface, the router would have complained. It would have failed an RPF check or reverse path filtering check, and then dropped the traffic because it has no need for it and it's invalid. And that basically stops you from looping around a layer 3 network and flooding that state. That's how we prevent loops. And those are the fundamental building blocks, and those are the bits that I'm going to talk about today. So we, as I mentioned, we have these multicast ranges and multicast addresses. And so those are in the standard format of an IPv4 address. There is multicast with inside IPv6, but yet again, IPv6 is a more complicated topic, so it's out of the scope of this talk, certainly for today. But standard IPv4 format addresses are used for multicast ranges, and those specific addresses are specifically reserved for the use of multicast. So if you try and use one of these addresses and assign it to your Windows machine, for example, on your interface for that, or on your normal Wi-Fi or your Ethernet connector, well, then that's not going to work. It's going to give you a little error that says this is an invalid address or something along those lines. It's going to look valid, sure, but it's going to be an invalid address because it knows in the background, well, this specific range of addresses, this 224/4 range is reserved. And so there's a range of different ranges. I'm not going to say all of them because we'll be here forever, but I'll give you an insight into what these are. So the first one here is used for local layer 2 use, effectively. And it's mostly used for kind of control of protocol operation. So there's a lot of well-known multicast addresses in there. So there's an OSPF one, there's a PIM one, there's some EIGRP specific addresses there. There's a lot of reserved addresses there, basically. We then have another one that is used for random use, specifically in session announcement protocols. We then have another specific block, which is used for source-specific multicast. And so source-specific multicast allows you to combine that multicast address with a specific source address for that multicast stream. Now, I can't personally think of too many real-world examples or examples that we could compare to from the actual real world, but one good example and use case of this source-specific multicast block is to provide a little bit more reliability and security in how you are requesting your multicast across the network. Let's say you have a multicast network that is moving around very fat flows of, let's say uncompressed video feeds. Those could be in the region of 10 gigabits per second, for example, depending on your resolution and the quality of the video that you're passing around and any extra data that you're passing with it. In a network where you've got those kind of flows moving around, you don't want a random device accidentally connecting to that source or that multicast address. You want it to be very specific and say, okay, I want to join this address sourced from that specific device. And so okay, I'm going to connect to this camera feed, which is the specific group address, and I want it from that specific camera, for example. And so explicitly when you request that traffic, you are getting the right thing. And so that's the concept slightly of the source-specific multicast block. In general, though, it is just there to make sure that you can specify where your source is, and it can make some things a little bit easier as well with the setup of that multicast tree that you have from source to destination and that forwarding of traffic. Anyway, moving on past the next two because they're a little bit more complicated. We then have finally a locally significant block of multicast ranges. And so what this allows you to do is, let's say, a studio production wants to use a range of multicast addresses for their media traffic, for example. That studio could use that range locally. They could not then send it out onto the internet to somewhere else, or they should not send it over a shared link to another company. That should be remaining locally within inside your network, maybe translating into a different multicast address at some point to then go out of your local network. But these should be restricted to local use only. They shouldn't be leaving your local company network, let's say. So those are the multicast ranges. Yet again, I go into a little bit more detail on the specific training for IGMP and PIM. So if you want more detail, take a look. Anyway, moving on to IGMP. So IGMP, as I mentioned before, is that membership protocol that says this device is interested, this one is, but none of these others are, or at least you know explicitly who is interested, and you can assume the rest of the network isn't. And so there are different versions to IGMP. There's a first version, a first implementation, which is very basic, and it will say this host can request, it can join, and we will then query to say, are you still interested? Are you still interested? Every few minutes. And if it doesn't reply to that question, that query saying, are you interested? We then stop forwarding traffic. And that's as simple as it gets with V1 effectively. Now, version 2 adds support for that destination to explicitly say, hey, I'm not interested in this anymore. Stop sending me it. What the router is going to do in the actual background is then going to say across the network, hey, is actually anyone else interested in this traffic, or can I stop sending? As a result, if something is interested, well, then it will reply back and say, yep, I'm interested still. And happy days, the router will still forward on the traffic. And if it's a layer 2 domain, well, hopefully you'll have IGMP snooping on board, and that destination that actually requested to leave actually doesn't get forwarded as traffic. If you don't have that concept of IGMP in there, well, then you might still be flooded the traffic, even though you said, hey, stop sending me the traffic. So that's V2. I should say, I'm looking at the headline functions between these versions. There are plenty of different tiny little differences in the RFCs, which mean that there is more to it than just these headline grabbing functionalities. So just bear that in mind. But then there is finally V3, version 3 of IGMP, and that specifically includes support for that source-specific multicast that I was talking about before. But if I recall correctly, V3 also allows for specific tracking of end host interest in an IGMP group. So not only now do you know, okay, someone behind this subnet or someone with inside this layer 2 domain is interested in my stream. Well, actually, host A, host B, and host C are interested, but host D isn't. Or at least you would know host A, B, and C are interested. Now, that doesn't help too much on actually how you forward the traffic, but it does help to actually, from an admin point of view, understand what is going on over the network. So that's a bit of an insight into, at least high level, those different versions of IGMP and how it works. But let's look at a little bit of a diagram. And before I get going, apologies, this diagram is slightly incorrect. An IGMP table does not know where the source of the traffic is coming from. All it's going to take is a state of what interfaces are interested and what the group is assigned to that. So please ignore this input interface with inside this table here that I've emulated. But anyway, we've got this very simple network here, a layer 2 domain split into 2 with VLANs, and 2 hosts here, and a multicast source demarked by a router. Usually, it's probably going to be the default gateway for these relevant VLANs. So what the end host does, it says, okay, I'm now interested in receiving multicast traffic. I've got this group, so I'm going to send an IGMP join to my default gateway. Well, the destination actually would be, the destination IP would be this specific multicast group. Now, because that group is outside of its local subnet, it's going to send at layer 2, it's going to send to the destination MAC address of its default gateway, which is going to be this router. If you don't understand what I mean by all of that, take a look at the previous L2, L3 video that I did to understand the concept of that default gateway and the concept of subnetting. That'll give you a bit of an insight into what I'm talking about. Anyway, this IGMP join is sent towards its local default gateway, and the router takes that state and stores it. Yet again, ignore this in field here. That does not exist in an IGMP table. We have then the multicast address against an output interface that has just requested. So in this case, we know something behind VLAN 10 is interested in this group here, this 239.192.1.1. So the router itself knows, okay, if I've got this multicast group traffic coming in, I want to send it out onto VLAN 10. So that's what that will look like. It's understand that control traffic that we just sent it, and now it's going to forward on the multicast traffic. Now, this is a good example of what I mean by IGMP snooping. In this case, A is the only one that is requested, but B has also got that traffic. That's an example of where we have no IGMP snooping, and that's because the switch has no idea who's actually interested in the traffic. What happens if we add snooping is that this device, B, when it actually starts up and starts to want requesting traffic, the logic in IGMP on the host side is that when you start up, regardless of whether you're receiving it, send out that IGMP join. And so that's going to facilitate IGMP snooping here, because regardless of whether it's still receiving the traffic, what it can do is it can shout up and say, hey, I'm interested, add my list, add my name to the list effectively. And so as a result, if snooping is running, it'll see that join coming in and start flooding out the traffic out of that interface as well as the other ones that have the traffic. So at this point, some time passes. I think the defaults are around 4.5 minutes or so. And the router will send out what is called an IGMP query. And what that is saying is anyone actually interested in this traffic? Yes or no? Just want to make sure that, I'm still supposed to be sending this traffic. So that is flooded out into the local domain, and these devices then process that and say, maybe, maybe not. And as we see in the next state, well, they both reply with a report. Actually, in theory, what's going to happen is when these end devices see this query message, they're going to set a timer, a random timer, which makes sure that either one of them will send a response at some point, but not immediately. And so the concept here is to, at least in V1 and V2, is to make sure that you don't have a flood of IGMP report messages from all of the devices on the network. In this situation, we've only got 2 devices that are interested, but imagine this is a network with 300 devices off it. There's going to be 300 reports sent to the router that the router then has to process, and that's not really going to be good for its processing power. It's going to probably get a little bit locked up, and it might impact service otherwise in other areas, sorry. So we set this random timer, and once that timer expires on that host, it will send. Now that report is sent towards the group address. So both the router will see it because it's outside of its local domain, but anything inside that local domain, that local subnet that is interested in the traffic will see it as well. Hence, once one of these end devices that still has that timer running sees that report message, it's going to end its timer and it's going to stop, and it's not going to send a report message. So that's how we report, and that's how we acknowledge, saying, hey, yeah, still want that traffic. Now, in the situation where no one sends back a report, a timer expires on the router, and then we end up with a state like this, where no multicast traffic is flowing through the network, and we don't have any traffic whatsoever, so we're not receiving anything. At this point, if A then wanted to start up receiving again, it would have to send a subsequent join and hope that the traffic starts flowing again. Now, what if actually A and B want to actually explicitly leave? They have no more interest in the video or the multicast source, so they send an IGMP leave message explicitly saying, "Hey, I'm not interested in that traffic." As a result, the router sees this, it processes it and says, "Okay, I acknowledge that, but I'm going to query just to make sure someone is still interested." So it uses that concept of the IGMP report again to send out saying, "Hey, actually," sorry, it uses the query, to send out saying, "Hey, is actually anyone still interested? Otherwise, I'm going to stop forwarding the traffic because there's no need. Someone sent a leave, so I'm going to assume everyone wants to leave." That's at least in V2. Remember, V3 has that ability to track host by host. So at that point, this IGMP table will be slightly different. It will track per device, is my understanding at least. And so it will say, "Okay, this host is no longer interested. Okay, no, I don't have any state for any other hosts, so stop the traffic." If it does have state for other hosts, well, then it just acknowledges that effectively and continues sending traffic to that local subnet because it still has devices that are interested. Anyway, back to the example where we're leaving. Both devices in this case are leaving at the same time somehow. So they both send the leave message. The router sends that query message to say, "Is anyone interested?" Okay, no one replies. And then we end up with that state where we've stopped the multicast traffic. And so that's just a very quick whip through on a bit of a IGMP process. I'm sure there's a lot more in-depth details there that I could go through. And if you watch the specific video on IGMP that I made, you'll have a little bit of better understanding of that. I go into a little bit more detail than that. But I think that is a good understanding there and an example of that normal IGMP operation. One thing that usually happens, and talking from more an operational point of view now, or a support point of view, is that it's very common, or I say common, one of the common issues that you'll see with IGMP and multicast traffic is that it'll work for a period of time, and then it will stop working. So maybe after a few minutes, usually around 4 minutes and a half, 4 minutes 20 seconds, that initial timer for this query message will expire. And then you'll stop receiving that traffic. And what's actually happening there is either the router is sending a query and it's not getting through the network to the end devices. So the end devices don't know that they need to send a report because they're not being prompted for a query. Or the router just flat out isn't sending a query whatsoever. It's faulty, it's buggy, it's not sending that. So yet again, multicast times out and then it drops the state. The devices then stop receiving the multicast traffic. Now, the other alternative is that a query is actually sent, but these end devices have no idea how to respond to a query for some reason. Maybe the implementation was never included in the code, and the 4-minute-ish timer expires, and then the router stops sending the traffic because it can't send that report back to the router. So that's just some operational side of some operational considerations to have when dealing with IGMP. Anyway, that's IGMP. That is your registration method. So we've talked about the address ranges, we've talked about the registration method, and we talked a little bit about loop prevention. The only other building block that we need to understand is routing decisions, and that's with PIM. And I'll talk through PIM because that's the most common option that we see. So PIM, Protocol Independent Multicast. It is used to route traffic across that layer 3 network. So as we mentioned in the last talk about layer 3 routing and dynamic versus static, it does require a normal unicast or normal IP routing table. Now, the definite recommendation here is not to use static routing when you're dealing with PIM. There's nothing stopping you. but genuinely, if you're using one dynamic protocol, PIM, with then static routing information, you could have a bad time. Unless your network is relatively small and very, very simple, then I would definitely recommend just sticking with the dynamic protocols to just make your life not hell, basically. So the way that PIM works is very similar to the likes of OSPF. And yet again, I've done a talk specifically on PIM to explain some of the technical details. I'll run through a very high level version of that talk, but if you're really interested in some of the technical details, go and take a look at that once you've ran through this. So the way that it works is it will form adjacencies between neighbors. And so those PIM-enabled routers need to be locally connected between just one layer 2 domain between them, and they can then form that adjacency between them. It uses that well-known local multicast, local subnet multicast group that we mentioned before, so that 224 range, to communicate across a local link connecting those two routers. And once we've formed those adjacencies, we can share multicast state across the network to induce the traffic flow between source and destination. And I'll go through what that looks like very briefly with a little bit of a quick diagram session after this. So, okay, we can share state, but well, how do we actually forward that traffic across the network? Well, there are two main modes, two variants. There is actually technically three, but I'll focus on the two because the third one is very similar to the sparse mode, the second one. So you've got two variants. The first one is dense mode, and as the name potentially suggests, it's going to be very dense. So what it does is it floods multicast, and that's why it's called dense. It's a dense concentration of the multicast across the network. It makes sure that every available router, PIM-enabled router within the PIM domain, receives that multicast traffic in some sense, so that it understands that exists in the network, and those PIM-enabled routers can then make their decision up to say, is someone requesting this traffic? Yes or no? No? Okay, at that point, we're going to then prune that traffic and say, hey, I'm not interested in it. Stop sending me the traffic. Now, that mode is very easy to implement, but it's not that resource efficient. Now, there are some cases where, yeah, it's probably fine to use dense mode. It's probably fine to have that flooding of multicast. Things like stock trading use multicast a lot, so that you have some kind of source of the actual share price, for example, and then you flood that share price across your network using multicast. People can then specifically request the details, and you'll occasionally get, the updated price. So it'll be a relatively small message, I would imagine. However, if you're dealing with some kind of media network, well, you could be dealing with 10 gig flows potentially. And the way the dense mode works is that it will initially flood the new multicast that it receives. So that could be a spike of 10 gigs of traffic across your network. It then sees the prune messages from the devices that aren't interested, so it stops flooding. But then after a period of time, a timer expires, and the original source of the multicast will then start flooding again to make sure that any router that doesn't really understand what he's doing has the opportunity to say, yeah, actually, I'm still interested, or no, actually, I'm still not interested, prune away. That concept can cause potential issues in your network. It can cause transient issues with congestion, errors, random utilization alarms if you're in an operations role. And obviously, these random spikes of traffic and potential discards and CPU utilization could throw someone in operations off. And they could see it and think, what the hell is going on? And think it's some kind of bug or spurious activity on the network, and potentially start trying to think about blocking it. Now, obviously, any network engineer that really understands multicast will probably understand what's going on and probably think, okay, we need to change that to sparse mode. But imagine that someone doesn't really understand what the hell PIM is or multicast is really, and they just see this traffic being flooded every 4 minutes or so. That's going to be really spooky for them, and they're going to think, oh, something's wrong. They're going to probably spend a bunch of time looking into it, and then they'll realize, oh, it's multicast. They've wasted a bunch of time. So realistically, the better way to implement multicast and PIM is using the sparse mode. Now, so the way that sparse mode works is you'll end up having what's called a designated router, and that designated router is the original router that receives the source multicast traffic from the actual source device. And so it registers it locally within inside its own PIM tables. And what it'll then do is it will register it at a central location within inside the network. And that'll be a standard routing device. But that standard routing device will be classified as what's called a rendezvous point, or an RP. And other PIM-enabled routers within inside the local PIM domain will know, hey, that's the RP, that's the rendezvous point. If I want some multicast, I've got to go and talk to him. So it's a well-known point in your network, and it should be something that is able to handle a large amount of traffic and a large amount of requests. So it can't be just some poxy device that you found sitting on the shelf. It needs to be something that can handle the traffic, because it's going to be potentially sent a lot of multicast. And so what happens is those requesting devices on the edges of your network will send a message to those RPs, those rendezvous points, and say, hey, I want some multicast, send me it. If the RP has that multicast registered in its tables, it will then forward the multicast on down towards those requesting devices. Now, if you're not following along with what I mean by sparse mode, that's not the end of the world. I've got a bit of a few diagrams showing exactly that operation. But that's the concept of PIM at a very high level, what it does and how it kind of works and what functionality it provides. Now, I mentioned about state. Well, how does that actually look on a routing table? Well, this is a bit of a high-level example. It's not exactly accurate, but I think it gets across the point to a certain degree. So the way that this diagram is structured is such that you have a source connected to this relevant device here, and you have relevant requesters connected to these routers here. As a result of the PIM joins, the IGMP joins that are sent from the end hosts, that IGMP state is then pushed into PIM, or PIM requests it from the IGMP protocol and says, okay, what is my outgoing interfaces? Well, that is Ethernet 2. Okay, happy days. It passes that state on to its neighbors, its PIM neighbor, and says, okay, hey, I have some requesters, send me traffic. As a result, the upstream device is going to say, okay, my outgoing interface list is now ETH1. I've added an interface. I've received what's called a PIM join across that message, across that interface, at least in the operation of sparse mode. But this state is the same regardless of whether it's dense mode or whether it's sparse mode. It has that concept of an outgoing interface. So it knows where it needs to send that multicast traffic. And these outgoing interfaces are related to a specific group. So we know for what groups we need to go out of what interfaces. This outgoing, this state is then passed on to this designated router here with the source, and it says, hey, okay, this device has an outgoing interface. Someone's requesting it from me, so you need to send it to me. And okay, this device actually has the source. So because it's received these requests from its neighboring routers, it knows that it's got outgoing interfaces. It knows where it's receiving the traffic from, so it fills in its incoming interface list and then starts flooding out the traffic towards those requested devices. Those devices then start seeing the multicast traffic, and then they start storing in their incoming interface list the interfaces where they're receiving the multicast from. And so from that, we can start storing this PIM state, and we can start understanding what's going on from an operational point of view. So that's a really high level point of view of the information sharing, but how does that actually look with sparse mode? Well, the following slides I've taken from the actual more detailed discussion around PIM. So if you want some more of these details, feel free to go and take a look, but I'm going to whip through these relatively quickly. So the concept here is that you have a source, you have this relevant network, and you have a requester down at the bottom, and you have that rendezvous point that I mentioned, or RP, that is your central point in your network. What happens is this DR, this router here, what's called a designated router, will then register the message, register the multicast traffic directly to this rendezvous point. This rendezvous point receives the traffic and then says, yep, okay, happy days, I've got that, I understand it, I know the state now. As a result, maybe some time later, the requester actually sends out its IGMP join or its IGMP report to its local gateway. Because of that, because it's PIM enabled, it says, okay, someone's requesting, I need to get that multicast. So I need to talk with the RP. Well, actually, what's going to happen is it's going to say upstream to its neighbor, hey, join this group for me. I need to join this group. I need to join this multicast group of 239111, for example. So it's going to send what's called a PIM join upstream towards the RP. The same device, same with this device, it'll say, okay, someone's requesting it from me. I need to talk towards the RP. So it'll send, hey, RP, there you go. I need this multicast. Send it me. The RP has that state, so what it's going to do is it notes the source, so it's going to send a join in the direction of the source. So this ends up back with the DR. The DR now knows, hey, someone's requesting my traffic. So what we end up doing is forwarding the multicast traffic on towards the RP, this router here, and then down towards the actual router that was requesting it and the end destination. Now, at this point, this router has actually realized the multicast traffic is coming from a specific source, because in the multicast traffic, we have a normal L3 header. It has the source IP and the destination IP, the same with the MAC addresses, right? But we're really interested in the IPs. So we look at the source address of this multicast traffic and realize it's this device here. Now, this device refers to its routing table and says, how do I reach this multicast source? Well, sure, I can go via this path, but it's a cost of what? It's 1, 2, 3, 4 hops, compared to potentially just 1 hop here, and then I've got the source. So what it does is it says basically, okay, sure, I'm getting the traffic, but a more efficient path is direct to this router. So it sends a join in that direction. Remember, that join is just very simply just saying, hey, I'm interested in this traffic. Send me the traffic in the direction that I've just sent you the join. It's effectively in reverse setting the path that multicast traffic should be forwarded at. So this source device sees that join, it starts forwarding the traffic. Now this end device has 2 copies of multicast traffic. It's coming directly, and it's also coming via the RP. Because it's now confirmed that it's receiving the traffic directly, what it's going to do is it's going to prune up towards the RP saying, hey, I'm no longer interested in the multicast traffic in this direction. Stop sending me it in this specific direction. So that's going to head up hop by hop towards the RP. And hop by hop, these devices are reviewing their PIM state, their outgoing interfaces, and saying, is anyone else interested? No? Okay, prune it away. I don't care. That will end up on the RP, and it will say, is anyone else actually interested? Well, no. So prune away back towards this designated router, because no one is interested in the multicast traffic. And at that point, right at the end, the normal state, once it's set up, is just very easily 1 hop, forwarding the traffic from source to destination. And that is PIM in a nutshell. That is that sparse mode operation very quickly ran through. As I mentioned, I've done a specific video on PIM and running through that operation and some of the technical details. So if this has sparked some interest or you want to know a little bit more detail, go and take a look at that video, and hopefully that will give you the information that you're looking for. Otherwise, hopefully you've enjoyed, hopefully you've learned something from this, and any questions, let me know, and I'll try and help out as best as I can. Otherwise, thanks for watching. Goodbye.